Okay, in this video we talk about the solution for the assignment of chapter 32, which is the Maxwell equation. Actually, in this chapter, we mainly talk about the magnetic version of the Gauss law, and which is even easier than the electrical version. Because there are no monopole of the magnetic. And also we talk about Ampere Maxwell's law, which involve a concept called the displacement current. So let's begin. So the magnitude of the E field between the two circular plates, this one, is E equals this expression in volt per meter. T is in second. At t equals to 0, E is upward. And the plate area is something like this. At t equals to 12.5 millisecond, what are the magnitude and the direction of the displacement current between the plate? And is a direction of the induced magnetic field clockwise. So there will be an induced magnetic field counterclockwise or clockwise in the figure. So actually in chapter 29 we know that the Ampere's law is something like this. The circular integration of the magnetic field over a contour or an Ampere's law will be mu 0 I enclosed. This is the current enclosed by the path, and so this is Ampere's law. And in this chapter we know that we also should consider another term called the displacement current, which is something like this: mu 0 epsilon 0, and we have a d phi e. Phi e is the electric flux dt. The first derivative of the phi e multiplied by epsilon 0. So if we just factor out mu 0, we will have I enclosed is the current in common sense. And actually we have another term, something like this. The derivative of phi e with respect to time multiplied by epsilon 0. So in this case, this term has the same dimension as a current, and we actually call it the displacement current. This is not a normal current in common sense, but actually it's something like a current going through a capacitor. And in the lecture slides, I've already told you, assuming a parallel plate capacitor, you can simply divide this term is something like the C dV dt, something like that. And okay, so actually, and according to this Ampere's law or Ampere Maxwell's law, we know that suppose the right hand side is positive, then there will be a induced magnetic field something like clockwise if the right hand side is larger than 0. If it is negative, then it will be clockwise. So actually, we would like to calculate the displacement current. So actually, this is nothing but epsilon 0 d phi e dt. So it is epsilon 0, and in this example, phi e should be always E dot dA, and actually this is a parallel plate capacitor. So A is a plate parallel to the capacitor. So E and dA are in the same direction. So E dot dA is nothing but EdA, and A is actually a constant, so it is nothing but E times A. So A is not a function of time, so we can just factor out A, and then we have a dE dt. And then we can substitute this expression here. So we have epsilon 0 A and d dt. First term is a constant, so after taking the derivative it will be 0. So and the next is 1.0 times 10 to the 5th power cosine 100 pi t. So in this case, we make some simple calculation. Epsilon 0 is actually 8.85 times 10 to minus 12, and A is 4.0 times 10 to minus 3, and then next is this term. This term taking the derivative will be 0, which is a constant taking a derivative will be 0. And then the next one, we have this term, 1.0 times 10 to the 5th power, and then taking the derivative of this one, which is minus 100 pi sine 100 pi t, which means that we take the derivative of the cosine, which will be minus sine, and then the chain rule of 100 pi t, so we multiply minus 100 pi here. So we have something like this, and actually it would be minus 1.11 times 10 to minus 6 sine 100 pi t. Okay, so next we substitute t equals to 12.5 millisecond into the expression, so it will become minus 1.11 times 10 to minus 6 sine 100 pi times 12.5 times 10 to minus 3. And be careful that this is in radian. So and actually the answer would be 7.85 times 10 to minus 7 A. This is a displacement current, although it's not a normal current, but at least the SI unit should be ampere. So we know that ID is a positive value. ID is a positive value, something like this. So So this is for part A. And for part B, as ID t equals 12.5 millisecond is positive. In this case, ID is upward. ID is upward, which means that it looks like there is some current. There is some current going. There is some current ID going into the plate, and something like this. So finally, for part C, what is the direction for the induced magnetic field? And the reason is the same. ID is ID for t equals to 12.5 millisecond is larger than 0, and using the right hand rule, okay, this is positive, which means that the direction going upward is positive, as long as you have E is positive when it points to the upward. So you use your thumb of your right hand to point to upward, and then something like this. Then you have several fingers like this, and then your finger will point to counterclockwise direction. So actually, by right hand rule, the induced magnetic field is counterclockwise. Okay, so this is pretty simple question. This is a pretty simple question. And okay, so the next one in my opinion is still very simple. Actually, when you consider the step, there are not much steps, but actually this is actually you need to understand what is a line integral, and you need to familiar with the Ampere's law. Then you can solve this very easily. So let's read the question first. An infinite long wire along the z-axis. So this one is the infinite long wire going to infinity, and carry a current I0 in positive direction as shown. So as long as you have this information, then you know that there will be a magnetic field equals to something like 2 pi r mu 0 I0, something like this. There will be a magnetic field, and the magnitude and direction depends on the position. And in this case, we define a magnetic field by this current, and we define another path which is called S, is defined to be ABC, showing here. So A is A minus B0, B is Z0D, and C is AB0. So actually these two has the same x-axis, And for a y coordinate, they are the absolute value are the same, but with different signs. And for z coordinate, they are all 0. And this is another point. Actually, midway between them, but actually this point is not really important when you when you look at the answer. And here A, B, C, D are all positive number. Find the line integral BDS, where B is the magnetic field generated by the current I0. So actually, the problem design here is not to require you to directly do the line integration, but at least you need to know what it means by the line integration. Actually, when you do the line integration from here to there along this path, which means that dash is suppose a B field. Maybe I should use another color. Maybe there is a B field, something like this. Not necessarily rotational or any form, but actually when you need to do the line integration, maybe I call this one C, from A to B, which means that suppose at this point we have B at this point like this, and then we should have another vector, maybe we can call it ds, which is going along this line, and ds, the magnitude is a very small number, and the direction should be the tangent line to the curve. ds should be the tangent line to the curve. So actually, you can do the B dot ds. Dot is the inner product, so you should be able to know to calculate that, and you calculate this for every point on the line, and then you add all of them together. Then it is the line integration, the line integral. But actually, you don't really need to do it in this problem. So here, let us consider something like this. Maybe we can draw another figure like this. So we assume we have a circle, something like this, because for magnetic field it will be symmetric. It will be symmetric because this is a cylindrical coordinate. Suppose this is a x direction, this is a y direction, and the z direction is out of the page. And hopefully we will have a point A here, point B here. So it will be A, B, 0, and here A minus B, 0, and C is should be somewhere here. Should be here. Actually, it is not on this plane, but actually out of the page. I cannot I cannot draw it here. Actually, it should be out of the page with the height d. So there is a height here. So actually, it's not on this plane. It is d on top of this page. So so the path we want to calculate is something like this, but something like this, and this path we call it S. But actually, we can assume an Amperean loop S1. So we call this one S1 of a circle 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 with no, on the xy plane, we give with the center at the origin, and radius, r equals to a squared plus b squared, and then take the square root. So it looks so long, but actually we only assume S1 is the whole circle. Is the whole circle here in blue. So according to Ampere's law, we know that the closed line integral b ds along S1 should be mu 0 I 0, right? It is very simple. So next we would like to consider that we consider the path from here, the A point, to here on the circle S1. So which means that S something like this. This is not B, this is C. This should be C. This point should be B. So in this case, we have B dot ds over the path S, which is what we want to find in this question, and plus B dot ds from the arc C to A, it should be 0. Also, according to Ampere's law, because you can consider that maybe I should use black. Okay, so you start from the point here. So you go in this way, go in this way, and then go in this way, and then through the arc going back to here. So this is another Ampere's law. This is an Ampere's loop. This is another Ampere's loop, and the current enclosed by this loop is of course 0, because the only current is here. So this current doesn't go through this Ampere's loop. So on the right hand side, it should be 0. And then we can write that as B dot ds should be minus B dot ds CA, right? Very simple. So actually we only move this term to the right hand side and do nothing. And then we can write that from A to C should be negative the same integral from C to A, because line integral is directional, because when you consider a path C like this, and then you calculate maybe B, ds is more or less the same direction. But when you consider you going backward, so we still have B in the same direction, because you actually integrate the same stuff, the same vector field. However, in this case, ds should be in the opposite direction, which means that if your integration is going backward, then you should have multiplied by -1, something like this. So okay, should be something like this. And so we just stop here, and then we just go back to this line integral. And as we know that for this one, B dot ds over S1 equals to mu 0 I. Actually, we know that the magnitude of B is uniform along S1, although the direction are different, but actually B dot ds, B and ds are also in the same direction, and it will become BDS, and B is always is a constant along this path, which means that when we consider when we consider the BDS along the arc AC, it should be proportional to this line integral. However, we should multiply by something else. But what is this factor? We can go back here, or maybe I can draw another one here. So we have This is the whole. This is the whole one. This is S1. And for arc AC, okay, something like this, and we can connect the original point to A and C like this. So we have the angle BOC and AOB are also known as theta. So actually the factor we need to multiply should be 2 theta, and for the whole circle is 2 pi. For the whole circle is 2 pi, which means that we go from here to here. So we go for 2 pi, but from A to C, we only go for 2 theta. So actually 2 and 2 can be cancelled, something like this. And what is theta? Theta is actually, we can calculate by this is A, B, 0, which means that theta should be arctangent B over A. So we substitute this one here, and also we substitute we also substitute we also substitute the line integration to be mu 0 I, so that S B ds, which is what we need to calculate, would be theta. Theta is arctangent B over A and over pi, and then this one is mu 0 I, 0. So this is the final answer. So as long as you know the Ampere's law and also the line integral, the calculation here is not so difficult. We only need this term, and we only need to calculate theta to be arctangent B over A, and then finally we multiply this factor 2 theta over 2 pi. Then the final answer look like this. Okay, so actually this is all the solution for this assignment, and if you have any further question, please let me know, and I'll try to reply to you, and I'll see you next time.